Welcome to The Explainer. Today, we are exploring a truly mind-bending concept that is literally reshaping the foundation of technology as we know it. We're looking at this incredible symbiotic loop that's forming right now between artificial intelligence and light-based hardware. We are talking about computers that process at the speed of light, built by the very AI that desperately needs them to evolve. It's a wild ride, so let's get into it. Our sources pose a really fascinating scenario. They say, imagine logic gates that run not on electricity, but on light. Now imagine designing them with artificial intelligence. Now I know what you're thinking. That sounds like pure science fiction, right? But I want to emphasize right out of the gate, this is not sci-fi. This is a real documented breakthrough from a massive 2025 study. Okay, so let's quickly outline how we're going to unpack this today. We'll start with the silicon speed limit, then we'll introduce photonic computing. After that, we'll see how AI is designing light hardware, how that supercharges artificial intelligence, and finally, what the hybrid computing future looks like. All right, let's kick things off with part one, the silicon speed limit. For decades, we relied entirely on electrons to power our computers. We pushed them through these tiny silicon transistors to represent data as ones and zeros. But here's the fundamental problem: physics. As we shrink these components down to the atomic scale, trying to make computers faster, those electrons face intense physical friction and resistance. It's kind of like trying to force a massive, panicked crowd of people through a single narrow doorway. The result? They generate a massive amount of heat, which requires complex cooling systems and ultimately hits a hard limit on performance. To put that into perspective, think about how traditional digital processors actually work. In digital systems, memory and processing are physically separated from each other, so data has to be constantly shuffled back and forth in this heavily synchronized step-by-step sequence dictated by a central clock. It creates a massive, sequential traffic jam. Even if you throw multiple cores at it, tasks are still largely being handled one after another. It's a deterministic bottleneck. Which brings us to part two. Enter photonic computing. This is the big paradigm shift. We are moving from the friction of electrons to the frictionless speed of photons. Instead of electrons facing resistance and generating crippling heat, we use light traveling through optical circuits. Photons experience virtually zero resistance. That means they generate almost no heat, and they can operate perfectly at room temperature. But here is the real game changer: wavelength division multiplexing. Because different colors of light don't interfere with each other, you can send multiple independent streams of data through the exact same pathway at the exact same time. We are literally replacing a hot, single-lane road with a frictionless parallel superhighway. Now let's move to part three, AI designing light hardware. As you can imagine, designing these intricate optical pathways is insanely complex. So researchers actually let artificial intelligence do the heavy lifting to engineer brand new hardware. Here are the exact 3 steps the AI took. First, scientists trained a neural network on over 500 simulated designs of a 2D grid made of gallium arsenide rods. Then, they used an algorithm called particle swarm optimization, which is actually inspired by how flocks of birds move in nature, to fine-tune the physical structure. Finally, the AI outputted a highly compact, all-optical XOR logic gate, and it operates right at 1.55 micrometers, which is perfectly aligned with the standard wavelength used in modern fiber optics. The absolute crucial takeaway here is this specific number, 17.947 decibels. Why does that matter? Because it proves the AI successfully engineered a simple, symmetrical optical gate with an incredibly solid contrast ratio. A logic 1 gives a strong signal, and a logic 0 gives almost nothing. And it does this without relying on any complex loops or nonlinear materials. It's just smart, ultra-efficient physical design, entirely powered by AI. Okay, let's flip the script a bit for part 4, supercharging artificial intelligence. So, AI built the photonic chip, but it did so because it desperately needs that chip to evolve. To understand why, we've got to talk about probabilistic computing. Advanced AI, like the computer vision making decisions in self-driving cars or diagnostic models in healthcare, can't just operate in absolute black and white. They have to estimate uncertainty. They need to know when they are unsure about a shadow on the road, for example. To do this, they rely on probability distributions. But remember, traditional digital computers are strictly deterministic, so they have to use clunky software to generate pseudo-random numbers. That fake randomness creates massive computational overhead and severely bottlenecks real-time, low-latency tasks. And this is exactly where analog architecture completely changes the game. Because information is encoded directly into a continuous physical quantity, like the actual intensity of a light wave, these systems natively offer the exact probabilistic output that advanced models like Bayesian neural networks absolutely crave. Instead of software struggling to fake randomness, the hardware itself provides it instantly. And photonics provides this randomness beautifully. There are three specific ways light naturally generates true physical randomness. First, we have phase noise, which is caused by spontaneous emission inside laser cavities. Second, there's intensity noise, derived from the chaotic beating of different frequency components. And third, we can even tap directly into quantum fluctuations by measuring weak coherent states on a single photon level. All of these completely bypass that whole digital bottleneck of fake software randomness. So what does this all mean? It means these physical properties translate into actual usable mathematical tools for the AI. We physically extract different probability curves directly from the light itself. We get uniform von Mises distributions from phase noise, Bose-Einstein curves from chaotic intensity noise, and Poisson distributions from quantum fluctuations. We are literally feeding the native chaos of light directly into the AI's calculations. This is how it actually comes together in the hardware. In a photonic crossbar array, that light-based randomness is injected straight into the physical structure of the neural network. You can mix coherent light with chaotic light or shape the optical bandwidth to precisely tune that probability distribution. Because the light just effortlessly flows through the system, the AI can perform massively parallel probabilistic calculations with sub-nanosecond latency. It is almost instantly assessing uncertainty. Let's bring this back down to Earth for part 5, the hybrid computing future. So when does this sci-fi sounding tech actually land on our desks? Well, we can't just rip out all our silicon processors overnight. Traditional electronic processors are incredibly cheap, they're well understood, and they're highly optimized for general tasks, like running your basic operating system. So the future really requires a complex hardware-software co-design. We need software that is hardware-aware. That means algorithms specifically trained to account for the inherent optical noise, temperature fluctuations, and fabrication quirks of these new analog photonic chips. Our sources lay out a very realistic adoption curve here. Right now, this tech is already being deployed in high-value, niche use cases. Think massive data center interconnects or automotive LiDAR systems for autonomous vehicles. By 2030, we fully expect to see broad integration of hybrid systems, computers that use silicon for the basics and seamlessly hand off the heavy, AI-driven parallel processing to photonic chips. And as for pure general-purpose photonic computing replacing silicon entirely, that's realistically still 10 to 15 years away, mostly because manufacturing processes need to scale up to reach cost parity. We've seen how AI uses its intelligence to design an optical chip, breaking totally free of silicon's limits. And we've seen how that very chip provides the lightning-fast, physical randomness that AI requires to process uncertainty, much like a human brain. It's this perfect, self-fulfilling loop. So, I want to leave you with this final thought to chew on. Does the future of true, human-like AI inherently rely on the chaotic, physical properties of light? Thank you so much for joining me for this explainer, and keep questioning what the future holds.